Welcome to this video. Today we will study basics of hybrid parameters or H parameters. So in the previous lectures, what we have done is basically DC analysis of different biasing networks. So in all those circuits, only DC voltages were applied, and we were interested in calculating the DC currents and DC voltages in different parts of the network. That we have done. So to do this analysis, we assumed that the transistor is in the middle of the active region, and the transistor was described by two simple equations: IC is equal to beta IB and VB equal to 0.7 volt, provided the transistor is in the active region. So this is about DC analysis. Suppose now we apply an AC signal to the transistor amplifier, then how to do the analysis when an AC signal is applied? So that comes under AC analysis of the amplifier. So to do the AC analysis of the amplifier, these two equations that I have written here are not sufficient. This corresponds to this IC equal to beta IB and VB equal to 0.7 volt is useful for doing the DC analysis. But for AC analysis, we need a more detailed model of the transistor, and there are several transistor models available. So what we are going to study is hybrid parameter model of BJT or H parameter model. So before going into H parameter model of BJT, first we have to study what is basically H parameter model, or what are the different H parameters. So we will see that. So I have shown a two-port linear network here. So keep in mind that it is a linear network. So it obeys the principle of superposition. So here I have marked the voltages and currents. V1 is the port 1 voltage or input voltage, and I1 is the current flowing into port 1. V2 is the output voltage, and I2 is the current flowing into port 2 or output port. So here please note that both the current directions are into the port. I2 is also flowing into the port. Okay. Current I2 is also flowing into the port. That is one point to remember. Then I have four variables here: V1, V2, I1, I2. So I can make two variables independent and two variables dependent on the other two. Okay, so there are different two-port network models like Z parameter model, Y parameter model, H parameter model, like that. So we will be discussing H parameter model. So in H parameter modeling, the independent variables are input current and output voltage. Okay, so input current I1 and output voltage V2 are the independent variables, and dependent variables are input voltage V1 and output current I2. So the dependent variables V1 and I2 can be expressed as a linear combination of the independent variables I1 and V2. I can write V1 as a linear combination of I1 and V2. So basically it comes like this: H11 I1 plus H12 V2. So V1 can be expressed as a linear combination of I1 and V2, where H11 and H12 are two hybrid parameters. Then similarly, the second dependent variable I2 can be expressed as a linear combination of I1 and V2. That is H21 I1 plus H22 V2. Okay, so these are the two H parameter equations, and I can write it in a matrix form also. So on the LHS, I have a column vector V1 I2. Then there is a coefficient matrix, and this right hand side column vector is I1 V2. So these are the independent variables, and these are the dependent variables. And this coefficient matrix will be H11, H12, H21, H22. So these four parameters are known as hybrid parameters or H parameters. So we will see why it is called hybrid. So to discuss that, first we will see how to find out these H parameters when a two-port network is available. From the terminal measurements, how we can calculate the four parameters. So to do that, first you can short circuit port 2. So if I short port 2, V2 becomes 0. So I have rewritten the first equation here. V1 is equal to H11 I1 plus H12 V2. Here I can make V2 equal to 0. So if I substitute V2 equal to 0, I will get H11 I1. So H11 is V1 by I1 with this condition V2 equal to 0. So what is the unit of this? It is a voltage divided by current form. So it is unit is it has dimensions of ohm. Okay, unit is ohm. Similarly, if you substitute this condition V2 equal to 0 in our second equation is I2 equal to H21 I1 plus H22 V2. So put V2 equal to 0. So I will get this relation H21 is equal to I2 by I1 provided V2 is equal to 0. So what is the unit? This is a ratio of two currents. So this is unitless. Now coming to the other two parameters. To determine the other two, now we have calculated H11 and H21. Now we have to determine H12 and H22. So to do that, you can open circuit the input port and apply the condition. So if I open circuit port 1, what happens? Current in port 1, I1 becomes 0. If I open port 1, I1 will be 0. So I have rewritten equation 1 here. V1 is equal to H11 I1 plus H12 V2. So if I1 is set to 0 in this equation, this becomes 0 plus H12 V2. So V1 is equal to H12 V2. So if I rewrite it, H12 is equal to V1 by V2 with this condition I1 is equal to 0. So what is the unit? It is a ratio of two voltages. So this is unitless. So we got H12. Now if I use the second equation, I2 is equal to H21 I1 plus H22 V2, and if I substitute this I1 equal to 0 criteria here, then I2 equal to, then it will lead to I2 is equal to H22 V2. So if I rewrite it, H22 becomes I2 by V2 provided I1 is 0. So what is the unit of this? Current by voltage. So it has dimensions of ohm inverse or Siemens. So if you look at the parameters, if you look at the dimensions of the different parameters, you can see H11 has dimensions of ohm, H21 is dimensionless, then H12 is dimensionless, H22 has dimensions of ohm inverse. So it is a hybrid collection of parameters. That is why the name hybrid parameters or H parameters. Okay. So by applying these two conditions, that is short circuiting port 2 and open circuiting port 1, you can determine all the four parameters of this two-port network. All the four H parameters of this two-port network can be evaluated. Now we can represent these two equations in terms of an equivalent circuit. So let us consider the first equation. So I have rewritten it here. V1 is equal to H11 I1 plus H12 V2. So look at this circuit which I have shown here. So if you apply KVL on this circuit, this particular circuit, if I apply KVL, what I will get? Source voltage V1 is equal to drop across H11. So I have shown a resistance with magnitude H11. So the current flowing through that resistance is I1. So the drop across this is H11 into I1. So V1 is equal to drop across this, that is H11 I1 plus voltage across this dependent source, that is shown here H12 V2. Okay, so it satisfies this equation number 1. So this equation number 1 is identical to this equivalent circuit. Here you can recollect that H11 had the dimensions of ohm that we have seen earlier. So it is modeled as a resistance, and H12 as a unitless parameter. So it forms the coefficient of this dependent source, dependent voltage source. Okay. Similarly, if you consider the second equation was I2 is equal to H21 I1 plus H22 V2. So if you apply KCL at this node, what you will get? The incoming current is I2 and it divides into two currents. So I2 is equal to sum of these two currents. So what is the current through this path? It is H21 I1. It is a dependent current source with magnitude H21 I1. So I2 will be equal to H21 I1 plus current through this resistance. The magnitude of this resistance is 1 by HO. So voltage across that resistance is nothing but V2. So what is the current? V2 divided by 1 by H22. Okay, so this is H22. V2 divided by 1 by H22. So it becomes H22 V2. Okay, so if you apply KCL, you will get I2 is equal to H21 I1 plus H22 V2. So this network represents the second equation. So if both V1 and V2 are measured with respect to a common node, I can simply join these two references without affecting the circuit. Okay, so this is the equivalent circuit of representation of H parameters. H parameter model of a two-port network. This is the H parameter model of a two-port network. Now, there is one more thing I want to mention. This H11 had the dimensions of resistance. So H11 is, if you go back to this definition, H11 is V1 by I1. So it is also known as driving point impedance of port 1. Driving point impedance of port 1. So it is also denoted as HI. I denotes impedance. Okay, H11 is also denoted as HI. Then if you look at H21, it is a ratio of two currents, and this is output current I2, port 2 current I2 divided by port 1 current I1. So it is also known as forward current gain. So it is denoted as HF. This is forward current gain, HF. Okay. Similarly, H12 is a ratio of two voltages, but this is input by output, or port 1 by port 2. So it is a reverse voltage ratio. So it is denoted as HR. And here this is H22 is I2 by V2. So it is current by voltage. So it is the driving point admittance of output port, and it is denoted as HO. Okay, so let us summarize it. So H11 is also denoted as HI, and H21 is also denoted as HF, forward current gain, H12 reverse voltage gain, HR, then H22 output admittance, HO. Okay, these are popular representation of these four H parameters. This notation is also used. Okay, then using this model, we can calculate some parameters of the circuits. First one is current gain. So here I have shown a two-port network, and on the input port I have connected a source with a voltage magnitude Vg, and the internal resistance of the source is Rg, and a load is connected on the output port. Load resistance is RL, and the current flowing through the load is IL. Okay, and you can observe that IL is actually equal to I2 with a difference in sign. I2 is flowing into the port 2 and IL is flowing out of port 2. Both are equal in magnitude but opposite in sign. So I2 is actually minus IL. So current gain of this circuit is output current, load current IL divided by input current I1. So IL is nothing but minus I2, we have seen. So minus I2 by I1. So what is I2? From H parameter model, we know that I2 is nothing but H21 I1 plus H22 V2. H21 I1 plus H22 V2. So divided by I1. So if you simplify this, this becomes minus H21 into I1 by I1 is 1 minus H22 into V2 by I1. Okay. So let us simplify this. So this is AI equal to minus H21. AI is equal to minus H21 minus H22 into V2 by I1. What is V2? So if you look at the circuit, V2 is the voltage across this load resistance RL. So it is nothing but ILRL. V2 is ILRL. So this is minus H21 minus H22 into IL RL by I1. And we have seen that IL is nothing but minus I2. So it is minus I2 by I1 into RL. And minus I2 by I1 is nothing but current gain. So it is also AI into RL. So you have AI on LHS and RHS, so combine that. So when you bring this term to the left hand side and take AI common, so AI into 1 plus H22 into RL is equal to minus H21. So AI is minus H21 divided by 1 plus H22 RL. And H21 is denoted by HF and H22 is denoted by HO. So AI is equal to minus HF divided by 1 plus HO into RL. That is the expression for current gain. We can now derive an expression for input impedance. So input impedance is V1 divided by I1 with all other independent sources in the network deactivated. But in our particular network, we have only one independent source, VG, and that is connected on the input port itself. So there is no other source to deactivate. So it is simply V1 by I1. We have to just take the ratio of V1 to I1. So V1 is H11 I1 plus H12 V2. This is from our first equation divided by I1. So when you divide, this is H11 into I1 by I1, that is H11 plus H12 into V2 by I1. Now what is V2? V2 is voltage across the output port, that is load current into load resistance, IL into RL. Okay, so V2 is IL into RL. And what is IL by I1? IL by I1 is nothing but current gain, AI. So I have written this H11 plus H12 into AI into RL. And H11 can be denoted as HI, as I have mentioned. Then H12 can be denoted as HR. Then it is multiplied by AI and RL. So this is the expression for input impedance. Input impedance is HI plus HR into AI into RL. So to calculate the input impedance, first you have to calculate current gain. So current gain can be calculated using the previous equation. Okay, then coming to the third parameter, it is voltage gain. Voltage gain is output voltage divided by input voltage, V2 by V1. And V2 is nothing but IL into RL, and V1 is I1 into Z in. V1 is I1 into Z in, because from the definition of Z in, we know Z in is V1 by I1. So V1 is simply I1 into Z in, that I have written here. So IL by I1 is, we have already seen, it is current gain. So AI multiplied by RL by Z in. So voltage gain is simply current gain multiplied by load resistance divided by input impedance. So if you have calculated current gain and input impedance, you can directly get voltage gain using this expression. Now coming to the fourth parameter, output admittance. Output admittance is defined as ratio of I2 to V2. I2 divided by V2 provided the all other sources in the circuit, that is VG is the other source, port 1 voltage source, that is deactivated. VG is set to 0. So I2 by V2 with the VG equal to 0. So I have redrawn the input port equivalent circuit here. So we have VG RG, that is the source. Then on the input side we have H11 and this dependent voltage source H12 V2. So if you apply KVL on this port, we will get this equation. VG is the source voltage, it is equal to drop across RG. Current flowing through RG is I1, so it is RG into I1 plus drop across H11, that is H11 into I1 plus this dependent source H12 into V2, that is also plus 2 minus, so the same polarity. Now VG is set to 0, so this becomes 0 is equal to RG plus H11 into I1 plus H12 V2, and we can write an expression for I1 by V2. That is, if you rearrange this, you can write it as I1 by V2 is equal to minus of H12 divided by H11 plus RG. Okay, So let it be equation number 3. Now we can calculate I2 by V2. So output admittance Y out is equal to I2 by V2 with Vg equal to 0. What is I2? I2 is H21 I1 plus H22 V2. This is from our H parameter equation divided by V2. And if you simplify this, this becomes H21 into I1 by V2 plus H22 into V2 by V2, that is 1. So I1 by V2 we have already determined. In the previous figure, you can see I1 by V2 is minus H12 by H11 plus Rg. Minus H12 divided by H11 plus Rg plus H22. So Y out is H22 minus H12 into H21 divided by this H11 plus Rg. Now you can use the other notation also. Instead of H22 I can write HO minus H12 is HR, H21 is HF, and this is HI plus Rg. So that is the expression for output admittance. So these 4 equations are important. Equations for input impedance, current gain, voltage gain, and output admittance. Using this you can solve numerical problems. Okay, we'll continue in the next class. Thank you.